In this series of videos I'm trying to offer advice to anyone that's getting started in electronics. The first piece of advice I would give is don't take my word for anything, go out and try these things yourself. In this particular video what I want to look at is the difference between a switching power supply and a linear power supply, and really why these switching power supplies came about and what their advantages are. They are of course much more complex than linear supplies, and it does sometimes raise the question as why do we go to all the time and trouble of creating such complex circuits when a linear supply would work and provide the same functionality for the target circuit. Firstly, apologies for any flicker on the display on the Kunkin electronic loads. There's some weird interaction between the lights in my lab here and the camera. Tried all the settings there are and I just can't stop it. So the circuits I have set up here by way of example are: on the right we have a very simple switching supply, and on the left a linear supply. Both are based around the same pass device, and this is a 2N3055 bipolar power transistor. The black tape on them, I'm not trying to redact anything, that's just so that I can use a thermal camera and get consistent results to see what their temperature is. The two circuits we have here, the linear supply is just equivalent to this, so we have the pass transistor, we have a driver transistor, and in this case we have some simple feedback to provide us approximately 5 volts on the output. The switching supply is obviously a bit more complex, and again we have the same pass device and the same driver, but in this case we're driving this switching circuit. So basically it switches on, puts energy into the inductor, switches off, the diode comes into play, and the currents alternate between being provided by the source or by the inductor. And again I've selected values here to give me a nominal 5 volts out. Both of the circuits are supplied with a 10 volt 3 amp supply, and in the case of the switching circuit I don't have any feedback at all. You'd normally use this as part of the basis for a switching supply with feedback. You'd sample the output and use that to control the frequency or the pulse width of the drive signal. In this case I've just got the drive signal connected to my signal generator, and it's running at 50 kilohertz, and all I'm doing here is supplying a series of pulses to the driver transistor. On the scope we're looking at the signal going in, so the blue trace is the signal we're driving this with, so that's this signal, and the yellow trace is the AC content of the output, so it's switched to AC and it's on 100 millivolts per division. So we're looking kind of zoomed in, if you like, at the AC ripple on the output. So I haven't done anything at all to optimize this. I've just pulled figures out of my head, thrown together a circuit, so it's not going to be very efficient, but even so we should see a marked advantage in terms of efficiency. And that's the first thing that we need to consider when talking about switching supplies. One of their key features is of course their efficiency. They don't require as much energy from the source supply as an equivalent linear circuit would. They do generate other issues such as noise. The circuits are more complex and need more components, although for large linear supplies the advantage swings towards the switching supply. Even though it's a more complex circuit, the components tend to be smaller and overall the design can be cheaper. Not only is it more efficient, but of course it draws less power from the source, which we'll look at as well, so it is environmentally friendly if you're into that sort of thing. There are other advantages, there are other disadvantages, but really I'm not going to go too deeply into this. It's a very complex subject. I'm just here going to show the fundamental difference between the two types of supply. We'll set them up both the same, so on the electronic loads are both set for constant resistance, So I've got them set up. The one on the left is the one that's loading up the linear circuit on the left here, and the one on the right is loading up the switching supply. Channel 1 on my O1 bench supply is supplying the linear side, and channel 2 is supplying the switching side. They're both set identically, they're both at 10 volts, 3 amp limit. And what we'll do is we'll start off by looking at the switching supply. So what I have to do here, of course, because there's no feedback, is each time I make a change to the load, I would have to adjust the pulse width of the drive signal just to get us back to the correct voltage output, which is a nominal 5 volts. So I'll turn the supply on. We're getting about 5.5 volts, so I'll adjust the pulse width to get us back down to 5 volts. So just slightly under 5 volts. Don't know if you can see the values on the display of the power supply. About 1/4 of an amp at 5 volts to our load. And if we get a calculator and work out the efficiency of this circuit, so we are drawing 1.22 watts or putting 1.22 watts into the load. If we divide that by the power being supplied, you can work it out, but it's 1.52 watts according to this supply. So 1.52, and that gives us an efficiency of slightly over 80%, which is not bad for something that's not optimized. I'm using a bipolar transistor as the pass device, which is not ideal for this sort of circuit, and the values are fairly arbitrary, but even so we're still getting a very good efficiency. Looking on the scope, we can see that we're getting about 50 millivolts of ripple. The spikes are, because of the setup I have, they're not actually coming out of this supply, so you can ignore these sharp spikes. What we're looking at here is this wider band, and we're getting about 50 millivolts peak to peak ripple. So that's fairly good efficiency. And moreover, if I get the thermal camera, if we look at the pass device, you can see it's barely getting warm. It's about ambient, so it's not even starting to warm up yet. If we change the load, so I'll change now, currently we are on 20 ohms. If I change this, and we'll set it to 10 ohms, we're now drawing half an amp. I need to adjust the pulse width to get us back up to 5 volts. Normally that would be an automatic feedback circuit, of course, so we're back up to 5 volts, half an amp, and that of course gives us 2.5 watts. So again, if we work out the efficiency, we're getting 2.44 watts into the load. This is showing us 3.099. And that's giving us about 79% efficiency. And despite us now drawing half an amp, if we look again at the pass device, don't worry that the crosshair is off center, it's not quite on the pass device, it does show off center slightly. So we'll find the peak, which is there, and that's about 22 degrees centigrade, so again barely getting warm. We'll reduce the resistance again, we'll go down to 5 ohms. We now need to adjust the pulse width again, of course, to bring us back up to 5 volts. We'll get the thermal camera. We are now starting to see some heat. Turn the camera back on. Some heat build up in our pass device, but even so, it's still only at 24 degrees, 25, 26 degrees. Let's try and find the hot spot here. So about 28, I thought I saw 28 there. So about 28 degrees, and that's drawing 1 amp, and this is with a 10 volt supply. We'll go down now, and I'll change to 2 ohms. Get us back up to 5 volts. Okay, so we're now drawing 2.5 amps. 10 volt supply, of course, still at 10 volts, and normally with a linear regulator would start to get issues You would of course normally have heat sinks on these, of course, but I'm trying to show the effect of the power dissipation. So again, with our thermal camera, we'll look at the pass device, try and find the hottest. So it's about 50 degrees centigrade. It's quite comfortable to keep my finger on there, it's not going to burn me, so there's hardly any heat being generated in this circuit despite us passing a reasonable amount of current. The other thing to bear in mind here is that the ripple is now up around 300 to 400 millivolts peak to peak. This is because we have a fairly low switching speed, and as I said, it's not an optimized circuit anyway. If we want to reduce this, what we can do is I'll change the frequency at which we are switching. So we'll go up to 60 kilohertz. We're at 45, so we're now at 60. I'll need to adjust the pulse width to get our voltage back to what it should be. And you can see that the ripples come down by about 100 millivolts, down now around 300 millivolts. And if we were to increase the frequency still further, then again the ripple can be brought down even more. You can optimize this if you design your own circuits. Okay, so what I'll do now is I'm going to turn the frequency back down to 45 kilohertz. Okay, so we're back down to around 5 volts. Ripple's gone back up, of course. But the point here is we can leave this running indefinitely at 2.5 amps, and we don't need a heatsink on the pass transistor. It's not going to overheat. It will be absolutely fine. What we'll do now is, just by way of comparison, we'll look at the linear supply. Before we do that, I'm going to set them so they're both the same, so we can do a side-by-side comparison. So we've got 5 ohms set on this electronic load, 5 ohms on the one that's connected to the linear version of the supply. We'll turn on the linear source, we'll turn on the load. Okay, what I'm going to do is turn them both off. I'm going to let them cool down to ambient, and then we'll turn them both back on. So we've got them both set at 5 ohms. I'm going to wait until they cool down, turn them both on, and we'll monitor them side by side and see what the effective heating rates are of the two devices. Remember, the load they're supplying is identical. It's 5 ohms in both cases, so it gives about 1 amp, and the source voltage is the same at around 10 volts. Okay, so both devices have now cooled down to approximately ambient, so around 23 degrees or so. The black tape I put on them should give us fairly consistent results between the two. As you can see, I've turned the left-hand breadboard around so we can have the two devices side by side. I've got both loads set to the same, so they're both on 5 ohms. And what I'm going to do now is power these up. Switch on the two loads. It's going to adjust the pulse width to give us exactly the same output, as close as I can on both of them. So very close. We're getting around 5.4 volts, just over an amp on both, and that equates to about 5.9 watts. The left-hand supply is sourcing nearly 11 watts. That's the one feeding the linear supply. And the right hand one is 7.8 watts, which again is another advantage. It's not just the efficiency that we are cutting down on dissipation, but we're of course drawing less power as well. So we'll look at the two devices. So the one on the right, the switching one, is already up to 27 degrees. The one on the left is already up to over 40. So that's after about 30 seconds. So we'll leave these going. Now of course you would have them on heat sinks, but even so, this is showing that the heat sinking you would need, the efficiency of the switching supply is much better. In fact, this video came about as a result of I was shooting a video for this series, which I'll be showing later, and it was about heat sinks and picking a correct heat sink for an application, and I decided this might be what might help in clarifying the situation with regard to heat sinking, and why something like the Ride supplies, although they're very high power, have very small heat sinks. That's of course because they're switching supplies and don't need huge heat sinks. So looking at the two transistors again, we've got about 33, maybe 34 degrees for the one on the right. The one on the left is now up to about 65 degrees. And remember, these are supplying exactly the same amount of power. The source supply is the same. It's just a matter of the efficiency in the way the power is being taken by the circuit. So we'll keep an eye on these. So the switching transistor, about 36 degrees. It seems to be sort of leveling out. It's going to, I think, stop rising fairly soon, around 37 degrees. And the one on the left, still rising. We're now up over 70 degrees. That's 75 degrees centigrade. Still climbing. And the one on the right, around 38 now, so 39, so it's still going up. We'll leave them for a few minutes and see what happens. But as I said, the point of this is if you're designing a system and you're considering your power supply, it is quite easy to design a switching supply that has reasonable efficiency. You can see here, just cobbling together a few basic components. Even a bipolar transistor, you'd normally use a MOSFET that's much more efficient in switching, has a much lower on resistance, but even something like a bipolar transistor, very old type of transistor we're using here, can give you reasonable results in excess of 80%. We'll get the camera back in, see what we're up to. So we are over 40 degrees now. This is the switching device. Turn the camera back on. Okay, so we're about 42 centigrade, but I can still easily put my finger on this. It's kind of warm to touch, but it's not hot. I'm not going to put my finger on the other one. That is now up in excess of 90 degrees centigrade. Okay, what I'm going to do now is turn them both off, let them cool back down to ambient, but we'll then increase the load and see what happens when we subject them to higher current output. So we'll change the resistance of both electronic loads. So our two pass devices are now back down to ambient, about 23-24 degrees. So I'll power up both circuits. Remember, we're now set to 2 ohms. I'll give us getting on towards 2.5 amps. The voltage will have dropped. I'm not going to bother adjusting the output of the linear regulator, so I will adjust the switching regulator to suit. There is a element of feedback on this already, but it still needs adjusting whenever the load changes. In terms of thermal management, although you can fit heat sinks to the linear version to keep the temperature of the pass device down, remember you still then have the thermal management of your overall device to consider. You've got more waste heat to get rid of, and so that's something that needs to be taken into account even if you decide to use heat sinks to dissipate the extra heat. Okay, we'll get these powered up. Got the output voltages set pretty much the same, so we're about 2.3 amps on both of the regulators. The left hand, the linear circuit is drawing just under 23 watts. The switching unit is drawing just under 18. We'll look at the pass devices. So we're up to 38 degrees already with the switching, and the linear is now up to 70 degrees, we're just coming up to, and this is about 20 seconds after power up. So 45 degrees with our switching device. We're now up to approaching 80 degrees linear. Back to our switching. The efficiency of the switching regulator has now dropped off quite significantly because the inductor, I wound it approximately for 1 amp, and obviously we're probably saturating that inductor with the way it's wound. But even so, you can see that the efficiency of the circuit is still pretty good. We're coming up now towards 60 degrees, just over, towards 65 degrees, whereas on the linear version we're approaching 115 degrees. So really whatever happens with the switching controller, switching regulator, we get far more heat out for the same output from the linear. So we're now approaching 130 centigrade for that one, and this one around 75, probably getting towards 80. Okay, so that's our switching device. So that's probably as hot as you want to really have it, whereas the linear one, I think it's time to terminate the test. We're up over 150 centigrade, so that would fail fairly soon. So you can see the effect that implementing a switching supply has. It's far more efficient. Even something as simple as this, we're getting efficiencies up around 80%, and the linear one, of course, there's no real efficiency in its conversion. It just dumps all the excess energy. So if you want 1 amp and you've got 10 volts going in, then you're going to dump the difference in power, so you're dumping 5 watts under those conditions, whereas with something like a switching supply you're probably going to be dumping less than 1 watt for a decent supply. Okay, well hopefully that all made sense. This is something that I would recommend playing with. Put these circuits together, design your own switching supply, compare it alongside a linear supply, see how you can optimize the switching supply. A lot of fun to play with as well. If you're into electronics, then switching supplies are quite a fascinating topic. If you implement feedback, which is quite easy to do, you just need to sample the output, and in something like this you can use that as the switching circuit itself, so the output can be part of your oscillator and feedback. So it is quite a fascinating circuit to work on, and the results you get can be quite remarkable. But you'll notice that something like the circuit we have here, even though we're passing quite a bit of power, it would have survived with a very small heatsink. We don't need a monster heatsink and forced air cooling. Whereas something like a linear supply, as your power level starts to go up, then your thermal management becomes much more of an issue.